Welcome back. This is in continuation with the last video lecture where we have discussed the other two types of ADC, the counter type ADC and the dual slope type ADC. This is the third type of analog to digital converter which is widely used in digital relays. This is often regarded as a flash type ADC in your text effects. Now, the major components of your flash type ADC are comparators, the flip-flops based on your logical gates, and a decoder. So, a flash type ADC, it is based on the principle of comparing your analog input voltage with a set of pre-reference voltages, reference voltages. And to convert this analog input voltage into a digital signal of, let us suppose, n bits, you do require 2 and minus 1 comparators. Now that we will look into this one. Now let us suppose if I do have a voltage, let us suppose it is somewhere around 3 volts. And if I want to convert into let us suppose a 2-bit operator, 2-bit digital data. You know, the 2-bit digital data can have 4 different options: 0, 0, 0, 1, 1, 0 or 1, 1, right? So for this one, what you will do is nothing but you will 3 volts data. We will compare it with 3 different sets of voltages. Now let us suppose if I make it as a let us suppose if I take it as 1 volt, 2 volt, 3 volts, and yeah. Now let us suppose if 3 volts, I use comparators here now. Okay, comparators, which is nothing but greater than or equal to, greater than and greater than. Now see, in this case now, what I will do is nothing but first of all I will compare with 3 volts. Now it is okay. It is 1. If it is this, again 1, again 1. So now based upon this, what I will give is nothing but I will give it as my output as 1, 1. Now let us suppose if it is only 0.5 volts. Now this is not greater than any of these things. So I will be getting 0, 0, 0. So I will take it as 0, 0. Now if it is greater than this particular one, first get, which means that this is my option. I'll take it as 0. If it is greater than this one also, then what I'll be doing, my bottom 2 gates will get on. So I'll take it as 1, 0. If it is greater than all these 3 things, then automatically I'll take it as 1, 1 and I'll mark it as 1, 1. This is the way how we do the things. Okay. So a quick, if you have not understood, let's have a discussion again. Now what I will do is nothing but to get 2-bit data, I will compare it with 3 different levels: VA, VB and VC. If it is less than VC, then now let us suppose these are connected to my switches. If it is less than VC, then all the 3 will be 0. If it is greater than this one, then only these 2 will be 0, this will become 1. And if it is greater than this one, only this one, these 2 will become 1, this will be 0. And if it is greater than this one also, then all the 3 will be 1. Which means my possible options are all zeros, 0, 0, 1, 2 switches on and 3 switches on. In this case, now if you carefully see, this I'll treat it as 0, 0, this I'll treat it as 0, 1, this I'll treat it as 1, 0, and this is 1, 1. So V input is compared with 3 different sets of voltages or any quantities, and then you are converting it into 2-bit digital data. See how many comparators you are employing now? That is 2 and minus 1. In this case, n bits means 2 bits. So 2 into 2 minus 1, this is 3. So 3 comparators you are employing. This is how it is being done. Now, so coming to the type of coming to the flash type ADC, as you have already seen that if you want to convert it into n-bit digital data, you do need 2 and minus 1 comparators. Now let's have a look at the operation. See, here in this case, 3 op-amps have been used as a comparators, and the non-inverting inputs of all the 3 comparators. Yeah, that I will show you first of all the block diagram. See, this is the block diagram which you do have. Now this is your analog input voltage. Now I do have 3 comparators. Now this is my reference voltage. What I am doing is nothing but I am dividing it using 4 resistors. Now this is my operating voltage. Now reference voltage, sorry. So I am employing this potential divider rule. So here I'll get 3 by 4V, 2 by 4V and 1 by 4V. Now this is being checked with all these voltages. Now see here, this is a comparator. If your V input is greater than 1 by 4V, then you will be getting an input signal here. If it is greater than 2 by 4, you will be getting here. If it is greater than 3 by 4, here. And if it is less than 1 by 4, you won't be getting any signal here. So which means that, see here, I will draw here. Right, this is my reference voltage. Since 4 are equal resistors, so here it will be V by 4, right? Here it will be 2V by 4. Here it will be 3V by 4. Now you need to compare your input voltage with all these things, right? So what I'll be doing is I'll be using a comparator here, right? So these points will be given to this negative terminals. Right. Now your input voltage, whichever, it is being compared with V by 4 here. Then if it is greater than V by 4, then only you will be getting an output here. 1. And here it is compared with here. And again here it is being compared with 3 by 4. So if your voltage, if it is greater than your 3 by 4, which means that this is passed, and this is also passed. Which means that your output will be 1, 1, 1. Right. If it is 1, 1, 1, then what must be your digital output? Your digital output must be equal to your 1, 1. Right. If it is 0, 0, 0, then it must be 0, 0. If it is 1, only this one is satisfied, and these two are not satisfied, then it must be 0. If both are satisfied, then so like this you are supposed to operate. Now how to get this type of logic, right? You are supposed to convert this logic into this logic, and here comes expressions. Now let's have a quick look about Now if you see that if Vn is less than V by 4, then all my C1, C2, C3, the comparator outputs are going to be 0. And for this one, I must get a 0, 0. And for anything between V by 4 to 2V by 4, C11 will be on. In this case, both will be on. And in this case, 3 comparators will be getting an 1 as our output. Now for all these 4 cases, this must be my digital output. 0, 0, 0, 1, 1, 0, 1, 1. Now I am supposed to realize this one using logical gates. So how easily, how simply we can realize them? That is our question. Now, is it possible for me to realize B0 with just a C1? No, it is not possible because there is no literal relation between these things, right? So I better stop this particular part. Now, one thing which we will do here. Now coming to C1 and C2. Now if you carefully see C1 and C2, is there anything which is similar? If you see, if it is 0, 0, then I am getting an output of 0. If it is 1, 0, I am getting output of 0. If it is 1, 1, I am getting an output of 1. If it is 1, 1 also, I am getting an output of 1. So what is your now amplification, what you have got? Now, if both are 1s, then only I will be getting a 1. Otherwise, I won't be getting any output of 1. So which means that B0 is a combination of C1 and C2. Right? If both are 1 only, then you will be getting a 1. If anything is 0, then I won't be getting 1 at the output. Right? So this is simply solved.
So how I can realize this one? I will just C1 and C2. I can directly go with an AND gate. Now coming to B1 now. Is it possible to get it with the C1? No, it is not possible. Right? They are nowhere linked. C2 also 0, 0, 0, 1, 1, 0, 1, 1, not at all linked. C3, now if you carefully see, this is also a little bit not linked to anything. Now we will take two combinations. Now, C2, C3 combination. Is it possible? If it is 0, 0, I am getting 0. If it is 0, 0, I am getting 1. If it is 1, 0, I am getting 0. If it is 1, 1, then I am getting as 1. So in this particular case, what I should do now? So which is the best option? Which is the best option which I can get now? Now if you carefully see, if it is 0, 0, I am getting an output of 0. If it is 0, 0, again I am getting an output of 1. If it is 1, 0, I am getting an output of 0. And if it is 1, 1, I am getting an output of 1. Which means that for this particular thing, I will be going with an XOR gate. And after that, I will be trying it with C1. Right? So an AND gate with the C1 is the best option. Right? So if I go like this, C1, C2, C3, see 0, 0, 0, this is 1, 0, 0, this is 1, 1, 0, this is 1, 1, 1. So what is C2 exclusive? If both are zeros, then it is 1, 1, 0. If both are same, then I will be getting a 1. Right? Since both are 0, I am getting 1. Both are 0, I am getting 1. Here both are 1s, I am getting 1. So both are same means I will be getting a 1 as well. Otherwise I won't get. Now this I will be getting 0. Now again what I should do? I should do compare with these things. If both are 1s only, I must get an output 1. This is 0, this is 1, this is 0, this is 1. Right? Which means that I am doing an AND gate. So which means that C1 and this is my gate of logical realization of B1. So this is what I have tried here, if you carefully see. C1 and C2 direct AND gate is B1, and this one is C3, C2, both are with exclusive gate, and again it is combined with C1 with an AND gate. Or otherwise you can solve it using your K-maps, which you have seen in the last classes. Okay. So now coming to the operation, I think you have understood now how it is being done. So I'm skipping this thing. So the features of this particular flash type ADC. This is the fastest type of ADC because the conversion is performed simultaneously through a set of comparators. So that's why it is often referred to as flash type ADC. And the conversion time is very, very less. It is somewhere around nanoseconds. So maximum of 100 nanoseconds or less you will be taking time for conversion of analog to digital output. And if you see, the construction is also very simple and very easy to design. So the problem with that is it requires, if you want to convert it into n bit data, then you do require 2n minus 1 of comparators. So that is a big problem. So if you want to convert your input to your, let us suppose 8 bit data, then 2 into 8 minus 1, it is nothing but 15 comparators you do require. So that's why it is not suitable for a higher number of bits in your digital output. And one more thing is that every time you increase the number of bits, more number of comparators is required, and it becomes a costlier and complex circuit. So it is not preferred for a higher number of bits. Okay. So I hope you have understood now, and I hope that now you are able to design your own 8-bit or 16-bit type of flash type of ADC. Okay. So on the whole, if you say analog digital converters are very simple circuits through which we can convert analog data to digital or quantifiable data. Because quantifiable data is always required for our processing. It is easier to process and also for store. And besides, it is very accurate and reliable by minimizing the errors. And we do require these ADC converters in our digital release. So that's it for today. In the class, we will solve problems on these different types of ADCs. I hope that now you are able to compare the operation of 3 different types of ADCs, the counter type, the dual slope type, and the flash type. And I hope that you will be able to design suitable ADC depending upon your given analog conditions, analog input conditions. Thank you. And these are the problems. Try to practice these problems at home and come back with the solutions to the class. Thank you.